when I open this up, I'll be at a computer with the browser that's been, I don't want to update the browser right now. So we'll just, you know, technology will always let you down. It will. Sorry, I'm becoming more and more of a Luddite the longer things go on here. Here's the picture I drew like second in class. Again, there's a link here. If you click on that and you had an actual working browser, you could get in there and move the point around and see how the tangent line changes. Let's see here. Here was the definition of limit point that I wrote Monday, right? And look, there's something else I talk about, an isolated point. If a point is a point in the domain and it's not a limit point, it's called an isolated point. And isolated points are what they sound like. They're points that don't have any other points in the domain close to them for a sufficiently small ball. Anyway, here's the picture I was trying to do to start class. But I don't know, this is both better and worse than what I did on the board today. Here's some examples of limits, right? So I tried to do things like that in here. Here's that definition of the one-sided limit I mentioned, all right? So these are the notes. I also have, for example, here's the proof. You're like, you keep talking about proofs. I don't care about proofs. I just want to know how to do problems. And that's okay. Just bear with me. But here's the argument that establishes that these two are actually equal. I have all of the details of that here, if you're interested. And again, if you're not, that's okay. Let's see here. So moving on, here are those pages and pages of epsilon delta proofs I mentioned that you can kind of skip over if you want. In fact, so here's the definition of vertical asymptote. There's also something called a hole in the graph. What would a hole in the graph be? I've drawn some today, but if you wanted to define it with a limit, a hole in the graph is a point where the limit of the function exists, the double-sided limit exists, right? And yet the limit point is not in the domain of the function. That's a hole in the graph. That's what it is. So, do you guys know how to put a hole in the graph of any formula that you want? Mathematical hole punch, do you know what it is? Here, I'll write here's the formula, f of x, all right? You guys give me any number you want to remove from the domain of f. I'll do it for you. What do you want? 7. Easy. Multiply by x minus 7 over x minus 7. Check it out. Now, the formula for g of x is not defined at 7, and yet it's exactly resembling f of x everywhere else. This will punch a hole in the graph. You just multiply by x minus the thing over x minus the point, wherever you want. If you want to put a hole, if you were so malevolent as to want to ruin someone else's perfectly good function and put a hole in it, just multiply by x minus c over x minus c. All right, moving on here. So here, right here, folks, is the proof of the limit of the sum is the sum of the limits, right? So the proof goes like this. I let epsilon be greater than 0. I pick a delta such that the f values are less than epsilon over 2 from the limit point for f, limiting value for f. I do the same for g. I make g within epsilon over 2 from its limiting value. I then pick a delta which is the minimum of these two things, which means that I get both of those estimates at once. Then I look at the difference of the sum of f of x plus g of x minus that sum. And by the triangle inequality, it's less than or equal to this plus that. But I've chose delta so that this is less than epsilon over 2, and that's less than epsilon over 2, which means in sum, they're less than epsilon, which proves that the limit of f of x plus g of x is equal to L sub f plus L sub g, and that is the adding limits formula. Now, where I used to work, there was a Chinese professor who taught Calculus 1 for the first time. He put this on the first test without warning the students. And it wasn't because he was trying to be mean. He just thought it was like an ordinary question. It was just a normal question for students. And I was like, no. You got to warn, if you're going to do that, you should warn the students at least, right? because this is not that understandable to people unless they kind of sit and dwell on it and meditate on it, right? So if you didn't understand what I just did, that's okay, right? But what you should certainly get from this lecture is the understanding that we can break a limit up. A limit of a sum is the sum of the limits, provided they both exist, all right? Now, that one's not too bad, actually. And pulling a constant out, the proof of that you can pull a constant out, if you look at this, it's really not much worse than the one I actually did, the linear function today. So you let epsilon be greater than 0. For c non-zero, you choose delta, which makes the difference between f of x and L less than epsilon over the absolute value c. And if you can do that, then because you can pull the c out, that c, absolute value c, cancels the other absolute value c, and we get epsilon, and that's the proof that you can pull a constant out of the limit. What follows, and I should also mention, once you have those two things, you can prove that this is called a linear combination. If you have like a sum of n things with constants, so this is sort of extending from just adding two things together to adding more things together. The point is, you can pull numbers out and you can break up across sums even if there's 5 of them instead of just 2. All right, it continues to be true. The proof here is by something called mathematical induction, which, if you're a math major, something it's worth looking at, right? Otherwise, you guys can kind of skip over it unless you're interested. Now, this right here is hard. The proof of the product rule for limits, I found this proof, like I tried to do it myself, and I have a proof in my old notes, which is more complicated. This I got out of a wiki book, but you can look at this. But it's actually quite difficult to prove that the product of the limits is the limit of the product, but the proof is here. Let's see here, anything else I want to tell you? So altogether, I would point out what we have. I hope I've explained to you some of the internal logic of this. Basically, anytime we have a polynomial, right? What's a polynomial? Something with this formula, right? Like a constant times x to the n plus da 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 plus a constant times x plus a constant, right? It's a linear combination of powers of x. It's a polynomial. That's the formula. If you have such a thing, what's the domain? The domain is all real numbers, right? We can plug in any real number into a polynomial, it works. We can evaluate, right? And the good news is the limit of a polynomial as x goes to a is just p of a. So when there's no division by 0 in the expression we're limiting, good news. We just get to plug in the limiting value. In other words, that weird thing about the tangent doesn't happen to us in the polynomial problem, right? You can just plug the limit point in. So Friday, I'll start looking at problems where we can't just plug the limit point in, right? We're going to get past these limit laws, and we're going to see how we can calculate limits that have where we can't just plug in the number. We're going to have to do algebra before we do it. So hopefully that's what we'll do. We'll do Friday. And of course, Friday we were over in the lab over there. So I'll see you there. I think we're done. Sorry if I've gone over. My watch, every so often my kids reset my watch, and